the magnetic force acting on a wire that carries an electric current is equal to ILB. That is, assuming the wire is perpendicular to the external magnetic field. Now, there are, within that wire, individual electrons moving that are causing a magnetic field. And that's ultimately what causes the magnetic force on that wire. We can calculate the magnetic force on the individual electrons in addition to the force on the wire itself. We're going to calculate the force on the individual electrons by using this equation. F is equal to QVB. Now, this equation assumes that the particle is moving perpendicular to the field, just like the equation that we learned a couple of days ago assumes that the wire is perpendicular to the magnetic field. Now, this equation is really the more general equation, because when we have a wire with an electric current going through it in the magnetic field, really all we have is a bunch of individual electrons moving through the wire in the magnetic field. Technically, each of those individual electrons have a force that could be measured or calculated by using this new equation, F is equal to QVB. But combined, when we combine all of those individual forces on all of those individual electrons, we get the total force on the wire, which is this equation. So although technically this is always valid, even in a wire when we have electrons moving through the wire, generally what I want you to do is when you have a wire, use this equation. When you don't have a wire, but rather just individual charges, use this equation. What does Q stand for? The charge. And the charge is going to be measured in coulombs. V stands for the speed. Don't get that mixed up with potential or potential difference. This is a lowercase v. And now that we're talking about magnetism and electricity and so on, sometimes we get mixed up speed and electric potential. This is speed, okay? The old-fashioned speed that we learned on the very first day of Physics 20 last year, measured in meters per second. B stands for the? Yeah, this is the external magnetic field strength. Not the magnetic field that's caused by the moving charge. There is one, but this is the external magnetic field strength, and the units for that would be Tesla. Fm, of course, stands for the magnetic force, right? Spencer, question? Somebody help him out there? What's this little symbol, this upside-down T? Cameron? Yeah, it just means perpendicular, so the particle must be moving perpendicular to the magnetic field. This equation isn't valid if that's not the case, okay? If they're parallel, there is no force, so you don't have to use an equation. Now, don't write this down, okay? Don't write down what I'm about to say here. If they're not parallel or perpendicular, you can actually find the magnetic field force by saying QVB sine theta. What you're really doing is taking a component of it, right? A component of the magnetic field. But that's not an equation that we have to know in Physics 20. Okay? By the way, if I did that, by the way, I shouldn't have erased that. If I did that, F is equal to QVB sine theta. Let's assume that they are perpendicular for a second. What's the angle going to be if they're perpendicular? 90. And what's sine 90? 1. So what does the equation become? QVB, right? The equation becomes QVB if they're 90 degrees, if they're perpendicular. That's the only special case besides parallel. By the way, what's the angle if they're parallel? 0 or 180. What's sine 0 or sine 180? 0. So what's the force? 0, right? Okay, those are the only two specific cases of that we need to know. So as far as equations go, just this one. Because when it's 0, there is no force. When it's 90 degrees, this is the force. All right, let's take a look at an example. Question number 1 says a proton is traveling at a speed of 5 times 10 to the 5 meters per second into the page through a magnetic field that's directed to the right of the page. Now, those directions are important because if the directions are parallel, there is no force. If they're perpendicular, we can find the magnitude of the force using the equation that we just learned and the direction using the hand rule for deflection that we learned about a couple of days ago. If there's something other than parallel or perpendicular, we don't know how to do this question, or at least we do, I guess, because we just did the equation, F is equal to QVB sine theta, but we don't need to know how to do this question. Are they parallel? Is a charged particle moving parallel to the field? No. Is it perpendicular? Yes, it is. That means that the equation that we just learned, that means that the hand rule that we've learned a couple of days ago are certainly valid here, so let's use them here. F is equal to QVB. Sometimes I forget to put the little upside down T, Spencer, but really I should put it in there to remind me that it's only valid if it's perpendicular. Now on your data sheet, you're going to see that upside down T, so they remind you of that on your data sheet as well. Q is charge of a proton 1.6 times 10 to the minus 19 coulombs. The speed here is 5 times 10 to the 5. And the magnetic field strength here is 2 times 10 to the minus 2. When I do the math there, it works out to be 1.60 times 10 to the minus 15 newtons. So the magnetic force on this is 1.60 times 10 to the minus 15 newtons. At least that's the magnitude of the force. How am I going to find the direction? I got 3 hand rules now, right? The wire grasp rule, I got the coil rule, I got the hand rule for deflection. Which one is it, the first, second, or third one? The third one, the hand rule for deflection. Whenever we're dealing with that external magnetic field, and certainly when we're dealing with magnetic force, you're going to use that third hand rule, the hand rule for deflection. So we're going to say thumb in the direction of the particle. We should have circled this in red to draw attention to the fact that it's a positive particle. Right thumb traveling into the page. Magnetic field directed to the right side of the page. Palm's going to point which way? Towards the bottom of the page. Good. You could say down the page toward the bottom of the page, but don't say down, because our frame of reference is not the Earth. The frame of reference is the page. Now I want you to take a look at example number 2. It says a 5.0 times 10 to the minus 25 kilogram particle with a charge of plus 1e is traveling out of the page through a magnetic field that's pointing to the right. Determine the speed that the particle must be traveling near the Earth's surface in order to not be deflected. Now, I want you to make a couple corrections to this question on your page because there's a couple typos here. Firstly, we're missing the magnetic field. Okay, we're missing the magnetic field. This is a magnetic field that's caused by the Earth, so its value is going to be in that range of 10 to the minus 5. We'll make it 5.0 times 10 to the minus 5. We're also going to change the mass of the particle. Instead of making it 5 times 10 to the minus 25, we're going to make it 5 times 10 to the minus 22 kilograms. Now, that's a question? No? Now, what is it that we're going to do in this question? Like, what is it that that's really going on in this question? What's our strategy? If we open our imaginary physics thesaurus, we saw a word that means the same thing as not deflected before. What was that word? Suspended, right? If it's suspended, if it's not deflected, if it's balanced, if it's maintaining the same height, then that means all of those things mean the same thing, that two forces have to balance. Which two forces do you think are going to balance here? Could be gravity and the electric force. It could be the electric force and the magnetic force. It could be really any two forces. Which two forces are going to balance here? Gravity and? Good. Gravity and the magnetic force. Now, gravity is m times g, and the magnetic force is q times v times b. We're looking for the speed that the particle must be traveling, so we're looking for the variable v right here. We'll rearrange that to solve for v. Again, that's little v, the speed, not the electric potential. I get mg over q times b. The mass of this particle is 5.00 times 10 to the minus 22 kilograms. G is 9.81 meters per second squared. I'm making it positive because everything I did from the beginning was magnitudes of forces, right? These two forces aren't really equal. The magnitudes are equal. Okay, the directions are opposite. So if I'm just setting the magnitudes equal, then I'm dropping all the negatives. Okay, we divide that by the charge, which was, what is the charge? Plus 1e. What is it? Yeah, 1 elementary charge, or 1.60 times 10 to the minus 19 coulombs. And we're going to multiply that by the magnetic field strength here, which we said was 5 times 10 to the minus 5 Tesla. So let's calculate that now. Let's say 5 times 10 to the minus 22 times 9.81. And let's divide that by, use some brackets on the bottom, because we don't want to divide it by 1.6 and then multiply it by 5 times 10 to the minus 5 without combining those two numbers, without putting those two numbers as one term. So brackets 1.6 times 10 to the minus 19 times 5 times 10 to the minus 5 gives us 613 meters per second. Or we're going to say 6.1 times 10 to the 2 meters per second. Now, that is low, on the lower end of a charged particle speed. We usually expect a charged particle to be like 10 to the 4, 10 to the 5, 10 to the 6 meters per second. But is it possible? Yeah. Sure it is. Sure it is. If we got 10 to the 9, is that possible? The biggest one we can get is 3 times 10 to the 8. If we get 10 to the 9, we're wrong. If we get 10 to the 2, well, that's not common to get a speed that low, but it's definitely possible. Right? Yep. Why did we change the mass? Let's take a look, now that we've done those two questions, at the rest of worksheet number 11, questions 9, 10, 11, and 12.